after reviewing 3 dynamic test procedures for MPPT evaluation, different MPPT algorithms were reviewed. Following this, the 3 typical MPPT algorithms were evaluated under the EN 50530 dynamic test procedure. So this is a overview of the presentation, and likewise it is also the structure of the article. So first there's the introduction to the dynamic test procedures, then a review of the MPPT algorithms, a description of the EN 50530 test procedure. I'll be referring it to as EDT for simplicity's sake here. And next we have the experiment results and the conclusion and outlook. So MPPT techniques, maximum power point tracking techniques, are crucial for PV systems because they allow the system to maximize the energy harvesting. So likewise, this MPPT has gained a lot of research attention and several different techniques have been proposed. So with this variety of MPPT methods, there is a need to define a proper, well-defined test procedure to evaluate the performance of different MPPTs. So a dynamic test procedure is especially required because it allows better insights into the performance of MPPT under real-life work conditions. So the different MPPTs that are considered here are the stepped day by day and EN 50530 dynamic test procedures. So we'll just go through the different test procedures briefly. So the step procedure is the most common procedure, and as you can see, it's a very simple setup. It requires a single power interface, and the test conditions, which is the changes in load resistance or in the irradiation, are fed in terms of stepped stairs. That is, a rectangular input is given. And while this is a very simple and cost method, it is not very accurate and representative of real work conditions. Next, we have the day-by-day dynamic test procedure. And as it can be seen from this image, it is a little more representative of real-life work conditions because the conditions are taken from the environment itself. But likewise, it requires a large amount of PV panels and power converters to implement this test procedure. So even though it is closer to the working conditions, it takes a lot of time to implement, and it is also a costlier method. And now we move on to the EDT procedure. In this procedure, the PV module is replaced by a PV emulator, and only one power converter is required to evaluate multiple MPPT algorithms. And compared to the step dynamic procedure, this EDT is a little more realistic and representative of working conditions because it adopts a slope irradiation changes opposed to the stepped changes. And further, this method can because it is using a PV emulator, it can be conducted indoors, thereby saving a lot of time. So this is just a comparison of the different dynamic test procedures. And here we can see why we have considered the EDT procedure for this study. And it's seen that it offers high accuracy with a short testing time because of it's able to run at all times of the day. Very simple to implement. And while it is not the cheapest method, it is overall very cost effective because it's accurate and very quick. So now that the paper had described the benefits of this EDT procedure, it is seen in the paper that this test procedure so far has only been applied to conventional MPPT methods, which is the P&O and INC methods. We'll get on to the MPPT methods a little later. So what this paper does is it provides a comprehensive evaluation of different MPPT algorithms and also compares the performance evaluation of 3 MPPT algorithms under this EDT procedure. And now we move to the MPPT review part. So this is just a basic principle of MPPT algorithms, which is impedance matching between the PV source and load using a DC-DC converter. So by altering the duty cycle, the operating point of the PV system can also be moved towards the maximum power point. So these are the different MPPT algorithms that have been considered in the paper. The ones that have been highlighted are those that will be considered in the EDT test. So I will just briefly go through these algorithms and then move on to the highlighted ones. So in the paper, first describes the fuzzy logic and parabolic prediction MPPT methods. So this fuzzy logic MPPT method is implemented using 3 stages, and it uses the error input, and the 3 stages can be seen in this figure here in the left bottom corner. So the first stage, the error input, and the error is given as the delta of P by V of the IV curve. So in the first stage, the fuzzification occurs, and next, based on a rule-based table, we get the fuzzified output sets. These output sets undergo defuzzification, and then we get the final output. So while this fuzzy logic exhibits good tracking, there is a risk of drift occurring, and this drift phenomenon will be discussed a little later with the conventional MPPT algorithm. FLC can be implemented without drift if delta I characteristics is included in the input. Next, we have the parabolic prediction method. And how this works is that it first requires 3 points on the PV curve. Using these 3 points, it is implemented into a quadratic polynomial equation. From this quadratic polynomial equation, another reference point is obtained using this formula found in the figure. From this formula, from this new reference point, the power from this new reference point is compared to those of the original 3 points. Following this, the point with the lowest power is dropped, and these next 3 points are considered. These points are then once again repeated in this process until the maximum power point is obtained. The drawback of this is that it requires initialization using with these 3 points. Next, we have the IV curve fitting and MPP locus methods. So IV curve fitting is similar to the parabolic prediction method. It also requires several IV points to extract, which are then used to extract the physical parameters of the PV system, and then to estimate its own IV curve. And from this estimated IV curve, the MPP is found. It should be noted that because the estimation and the real, there'll be a slight difference between the estimated IV curve and the real IV curve. So the system might operate at the estimated MPP, which will be slightly moved away from the original maximum power point of the system. So then we have the MPP locus method. So this is one typical hybrid step size method. Hybrid step size is where you implement a fixed step size as well as variable step size. And this MPP locus method relies on the occurrence of MPP being in a straight line across different irradiation conditions. And what that means is it can be seen in different irradiation conditions with the different IV curves for the different irradiation conditions. The MPP is occurring in a straight line. A straight line can be joined between these MPPs. So as when there is a sudden change in the irradiance, a variable step size is implemented to bring the operating point close to that line using trigonometric principles. Following this, a fixed step size algorithm is then deployed to find the specific MPP. And now we move on to the MPPT algorithms that are going to be compared in the EDT test procedure. So first we have the conventional or the most basic and most popular MPPT algorithms, which are the Perturb and Observe, P&O, and the Incremental Conductance, INC methods. So the principles of these two methods are seen in these two figures. So the first one is the P&O method. So it is quite simple to see when the delta P by V is greater than 0, it moves the operating point to the right and vice versa. And similarly for the incremental conductance, when delta I by V is greater than the negative I by V, which is the conductance value, it moves to the right and vice versa. So some of the characteristics of the P&O and INC methods. Both these methods are capable of making the correct movement towards MPP under normal operating conditions. However, a wrong step can occur under conditions of sudden increase of solar irradiance, and this will be shown in the next slide, what exactly is meant by wrong step. This is also known as a drift phenomenon. So this drift phenomenon can happen for both fixed step size and variable step size implementation of these P&O and INC methods. So it is also possible to add a delta I variable to the P&O and INC algorithms to achieve drift-free operations. So we can see that what exactly is meant by drift and wrong step. So we'll focus on the condition of irradiance increasing. So initially, the load line passes through MPP2. And then when the irradiance is suddenly increased, it is shifted to MP2, this point B. And it can be seen that when this shift happens, the condition of the P&O as well as INC MPPT algorithms will be met such that it shifts the point to the right. And this is away from the MPP. So this is away from the MPP, and this is known as the drift. And it can be seen here as well in these INC and both INC and the P&O methods, the drift occurs. So next we move to the beta method, which is also considered in the EDT test in this article. So it is a hybrid step method, and it is implemented using a variable beta. So the formula for this beta is found here. And then how it works is that first a range for this beta is defined. And how the range is obtained is it depends on the working environment of the PV system. So first the beta method will determine whether this beta value is within the range of beta, within beta min and beta max. If the value is within the set range, then it is close to the MPP. If it is outside this beta range, a variable step size will be deployed to bring it back into this beta range. And once it's in the beta range, a fixed step size P&O can be used to precisely locate the maximum power point. It's been seen that this beta method shows strong performance under different irradiation conditions and with partial shading. And we will also further see it in this EDT dynamic test. So this is it's seen that this drift does not occur with, this is for the MPP locus, but for both these conditions, it does not occur. There is no drift. So now we move on to the actual dynamic test, the EN50530 dynamic test. And in this article, two different sequences of the test were considered. 100% irradiance represents the irradiation at the standard test condition. So it can be seen that the change in irradiance occurs in a sloped manner, which is defined by this t, this time interval, and this pattern keeps repeating for n number of times according to the required test cycle. So in order to correctly determine the efficiency of the MPPT, first the PV model for the simulation has to be formulated. And the I and V relation for the PV model based on the EDT procedure is given below. So this is the ISC, which is the short circuit current, and the open voltage current, whose expressions are given below. And I naught is an irradiance dependent current, and the CAQ is also given below. So this EDT model has also been compared with the traditional single diode model, whose equivalent circuit is given here, just to see the difference of the IV curve. And it's observed that there is significant difference, especially regarding the voltage. So now we move on to the experimental part. So the proposed test bench is given below, and the MPPT algorithm is implemented in this D space. And the three MPPT algorithms that were selected, as mentioned, is the fixed step P&O with two different step sizes, a variable step INC, and a hybrid step beta method. And it can be seen, this is a representative of the different step size characters. So what is especially the paper tries to study is the effect of sudden changes in irradiance on MPPT performance. So this is the first set of results. It shows the power waveform of the EDT procedure for these three MPPT algorithms by comparing the theoretical power values, which is given in red, and the achieved value, which is given in blue. And this allows us to see the MPP convergence with increase and decrease of irradiation for each algorithm. And from this, it is evident that the P&O with the small step size shows very poor tracking of the MPP, whereas the beta method is able to track the MPP much better than the P&O. And it is also noticed that the P&O with this small step size is more prone to poor tracking with sudden changes and increases than the larger step size P&O. And now we move on to see how the tracking routines of each MPPT show the difference of the movement of MPT with increase and decrease in irradiation. And from here, you can really see how this slope EDT test condition, which is the slope increase and decrease in irradiation, really affects the MPPT performance. Because with the slope increase in irradiance, the effects of wrong step and drift are compounded. So we take the two extreme cases, which is the small step P&O, and we can see that with each increase in irradiance, this algorithm continues to drift the operating point further and further away from the MPP. Whereas with the beta method, every time the MPP is shifted away from the actual MPP, the load line is shifted away from the actual MPP, this method is able to correct it, and hence we see like a saw-like pattern. So from these figures, we can see make a slightly deeper investigation of the tracking performance of different MPPT algorithms. And specifically, we focus on the first irradiance increase. And we take the most extreme cases, which is the small step P&O and the beta method. So we can see with this irradiance increase occurring, this PNO continuously drifts away from MPP, whereas the beta method is able to stay close to INC. And as this increase in irradiation continuously happens, the load line of the PNO method is not able to change. Is not able to change. It continues at the same place. Whereas in the beta method, it keeps increasing. And now finally, we can see the energy generation and MPPT efficiency, which is given by this formula for the different tests and for the different test sequences as well. So we can see, although in all conditions, the beta method has the highest efficiency, even for the beta method, there is a difference in efficiency with the B sequence, which is, which is the sequence that has a higher increase in irradiance change. So now we'll go on to the conclusions and outlook of that this article has shown. So this article presented a review of dynamic test procedures and MPPT algorithms. And then it compared 3 MPPT methods with this EN50530 dynamic test procedure. And then the focus was laid on the step size characteristics for different MPPT algorithms and the effect of wrong step and drift with increased irradiance on MPPT performance. So with this paper, we were also able to see how the sloped irradiance input affects and highlights the effect of drift in a more realistic way than the step test. And it's seen that out of the considered MPPT algorithms, the beta method by far showed the best performance across all conditions. And now some things that could be addressed in future studies, we could consider more novel and different MPPTs with the EN50530 test procedure. And then we can also might have to address what exactly the difference between the PV model in these two, in the EN50530 and single diode model means in terms of the MPPT performance evaluation, how the performance differs using this model and the single diode model. And next, this model does not really show the considerations of partial shading. So, thank you.